Have you ever wondered how a quantum computer works? Quantum computing, it's the next big frontier in technology. It's a field that combines the principles of quantum mechanics with the fundamentals of computer science to create a new kind of computing power. To understand quantum computing, we must first dive into the strange world of quantum mechanics, where the traditional laws of physics take a back seat. In this realm, particles can be in two places at once, teleport across space, and even influence each other instantaneously from light years away. In the realm of classical computing, we're familiar with the concept of bits. They're the smallest unit of data and can be either a 0 or a 1. But in quantum computing, we deal with qubits. A qubit or quantum bit can be a 0, a 1, or both at the same time, thanks to a quantum principle called superposition. This allows quantum computers to process a vast number of possibilities all at once, making them incredibly powerful. But it doesn't stop there. Another quantum principle, entanglement, allows qubits that are entangled to be linked together in such a way that the state of one can instantly affect the state of another, no matter how far apart they are. This interconnectedness can lead to a dramatic increase in computing speed and capacity. Now, why does all this matter? The potential applications of quantum computing are vast. From improving weather forecasting to accelerating drug discovery, from optimizing financial models to breaking encryption codes, quantum computing could revolutionize numerous fields. But it's not just about the potential. Quantum computing is already here, with companies like IBM, Google, and others leading the charge in developing quantum computers and making them accessible for research and commercial use. So, how do we go about building one of these quantum computers? Buckle up, we're about to dive in. In the heart of a quantum computer, you find qubits. But did you know there are different types of qubits? Indeed, the world of quantum computing is as diverse as it is fascinating, with each type of qubit having its own unique features, advantages, and disadvantages. Let's start with superconducting qubits, the rock stars of the quantum computing world. These qubits are tiny circuits made out of superconducting materials. They operate at extremely low temperatures, colder than outer space, to maintain their quantum state. The beauty of superconducting qubits lies in their scalability and speed. They can process information at a lightning-fast pace, making them a top choice for many quantum computing projects. However, their need for supercool environments can pose a challenge. Moving on, we have trapped ion qubits. As the name suggests, these qubits are individual ions, trapped using electromagnetic fields. Each ion serves as a qubit, and they interact with each other through their electric charge to perform computations. The strength of trapped ion qubits lies in their long coherence times, which means they can maintain their quantum state for a longer period. However, scaling up trapped ion qubits can be tricky due to the complexity of controlling multiple interacting ions. Last but not least, we have neutral atom qubits. These qubits are individual neutral atoms, trapped using lasers. Like trapped ion qubits, they also interact with each other to perform computations. The advantage of neutral atom qubits is that they can be manipulated in large arrays, which can potentially lead to a higher computational power. But, just like their counterparts, they also face challenges in scaling and control. In summary, each qubit type comes with its own set of unique features, pros and cons. Superconducting qubits are fast and scalable but require extremely cold temperatures. Trapped ion qubits offer long coherence times but face challenges in scalability. Neutral atom qubits can potentially offer higher computational power, but also face difficulties in control and scalability. Choosing the right qubit type is a crucial first step in building a quantum computer. So take your time, do your research, and embark on this fascinating journey into the quantum realm. Now that you've chosen your qubit type, it's time to assemble your quantum circuit. At the heart of any quantum circuit is a chip, a small piece of hardware that houses your qubits. This is where the magic happens, where quantum bits exist in multiple states at once. Superconducting qubits, trapped ion qubits, or neutral atom qubits, each type requires a different kind of chip. So make sure you've got the right one for your chosen qubit type. Next up, we have the vacuum chamber. This isn't something you'd find in your everyday electronics. The vacuum chamber is where your chip will reside, providing an environment free of air particles that could interfere with the delicate quantum state of your qubits. Now let's talk about lasers. Yes, you heard that right, lasers. In the world of quantum computing, lasers are used to manipulate the state of qubits, essentially writing and reading information. Each pulse of light from the laser can change the state of a qubit, allowing us to perform computations. Finally, we have the light detector. This is a crucial component of your quantum circuit. The light detector measures the light emitted by your qubits when they change state. This is how we read the output of our quantum computations. These four components, the chip, the vacuum chamber, the lasers, and the light detector, work together to create and manipulate qubits, the building blocks of quantum computation. They make up the basic structure of your quantum circuit. Keep in mind, assembling a quantum circuit requires precision and care. Each component plays a vital role in the successful operation of your quantum circuit. You'll want to ensure everything is operating smoothly and efficiently. With your quantum circuit assembled, you're ready to start programming. Just like a classical computer, a quantum computer needs instructions, and that's where quantum programming comes in. Now that you've got a handle on quantum mechanics and have chosen your qubit type, it's time to take a deep dive into the world of quantum programming. The quantum algorithms you'll write are the magic behind the machine, instructing your quantum computer on how to perform computations. One popular quantum programming language is Qiskit, developed by IBM. Qiskit is open source and designed to work with superconducting qubits, making it a great choice for beginners. It's also compatible with Python, a widely used programming language which further broadens its appeal. But what exactly does quantum programming entail? In essence, it's about creating quantum circuits and algorithms to harness the power of quantum phenomena like superposition and entanglement. A quantum circuit is a series of quantum gates or operations that manipulate qubits. These quantum gates are the building blocks of your quantum algorithms. While classical computing uses binary code, quantum programming uses quantum bits or qubits. Unlike binary bits, which can be either 0 or 1, qubits can be both 0 and 1 at the same time thanks to a quantum property known as superposition. This ability to hold multiple states simultaneously is what gives quantum computers their immense processing power. Learning quantum programming is an essential part of operating a quantum computer. Through it, you'll gain a deeper understanding of quantum mechanics and how quantum computers work. Plus, it's through programming that you'll be able to experiment and test the capabilities of your quantum computer. It's important to note that quantum programming can be challenging, especially if you're new to the field. But don't worry, there are plenty of resources available, from online tutorials to community forums, to help you navigate this exciting realm. So whether you're looking to solve complex problems, simulate quantum systems, or just curious about the quantum world, learning quantum programming is a fascinating journey that opens up a universe of possibilities. Remember, programming is the bridge between your quantum computer and the classical computer. It's the language that lets these two very different systems communicate and work together to perform computations that are beyond the reach of classical computers alone. It's time to marry the old with the new, connecting your quantum computer to a classical computer. This union allows you to control and communicate with your quantum computer effectively. Think of your classical computer as the command center, directing the quantum computer's operations. Now, how do we facilitate this communication? With the help of a programming language and a library. Python is a widely used language that's easy to learn, making it an excellent choice for this task. Coupled with Python, we have Qiskit, a library developed by IBM, specifically designed for working with quantum computers. With Qiskit, you can create quantum circuits, run experiments, and even simulate quantum computers. It's like having a quantum sandbox at your fingertips. So roll up your sleeves and start coding. With your quantum and classical computers connected, you're ready to start experimenting. Building a quantum computer isn't just about assembly and programming, it's about learning and experimenting. It's a journey of discovery where each step forward is a leap into the fascinating world of quantum mechanics. Your first quantum circuit may be simple, perhaps a basic quantum gate or a 2-qubit operation, but don't let the simplicity fool you. Even these rudimentary circuits can exhibit the extraordinary properties of quantum phenomena. As you gain confidence, start to design more complex circuits, explore different quantum algorithms, experiment with entanglement, superposition, and quantum teleportation. Don't be discouraged by the complexity or the inevitable mistakes. They're not setbacks, but stepping stones to your understanding. Growing your knowledge in quantum computing is a continuous process. Each experiment, each result, is a new piece of the puzzle. And with every piece, the picture of quantum computing becomes clearer. Remember, building a fully functioning quantum computer is a challenging task, but every step you take brings us closer to the quantum computing future. We've taken a whirlwind tour of building a quantum computer. We started by learning the basics of quantum mechanics and computing, then moved on to choosing our qubit type. We assembled our very own quantum circuit and even dabbled in quantum programming. Finally, we connected our quantum setup to a classical computer, bridging the gap between the old and the new. Thank you for joining us on this quantum journey. If you enjoyed the video, hit that heart button and drop a comment below. Until next time, keep exploring the quantum universe.